All right. So now at this point, hopefully you watched the lecture about the theoretical piece of the sampling distribution, and you've attempted these example problems, and you are ready to see the answers. So this first set of questions really just demonstrates the relationship between the standard deviation and the standard error that you saw in the previous lecture. So let's go ahead and work this out, and then I will explain how this demonstrates that concept. All right, so we have a population of drivers with a mean of 10 speeding tickets and a standard deviation of 1 speeding ticket. So looking at that, just as a review, you know that if it's a normal distribution in the population, 68% of drivers have between 9 and 11 speeding tickets. All right, moving on. So if you randomly select 10 drivers from the population, how well on average would you expect the sample to represent the population? Or in other words, how far away would you expect the sample mean to be from the population mean just due to random chance? Both of those statements are asking you, what is the standard error? Because that's precisely what the standard error tells you. It tells you the expected difference between any given sample mean of a specific sample size from the population mean. Okay, so let's calculate the standard error using the standard error formula. So the standard error is equal to the standard deviation divided by the square root of the sample size. Well, in this case, the standard deviation is 1 and our sample size is 10. So let's go ahead and solve for the square root first. We end up with 1 divided by the square root of 10 is 3.162. And 1 divided 3.162 is equal to 0.316. That is our standard error. So what this tells us is with a sample of 10 drivers from a population with a standard deviation of 1, we would expect our estimate of the population mean of speeding tickets based on the sample to be off on average by plus or minus 0.316 speeding tickets. So if you think about it, if we look at our mean, so 10 plus 0.316, and then remember plus or minus 1 standard error from the mean, so 10 minus 0.316. So 10.316 would be the high end of where most speeding tickets would fall from a mean of 10 scores. And then 10 minus 0.316 gives you 9.684. So with a sample of 10 drivers, we would expect their mean to be between 9.684 and 10.316 speeding tickets, because that's one standard error above and below the mean. Okay, moving on to the next example where we have a higher standard deviation, so more spread of speeding tickets in the population. So now our standard error, we're still looking for the standard error. How well on average will the sample represent the population? Or, how much of a difference would you expect between any given sample mean from 10 people and the population mean? So we've got our standard error formula. Now our standard deviation is 5, but our sample size has not changed. It's still 10. So this becomes 5 divided by 3.162. And you end up with 1.581 for your standard error. So, with a sample of 10 drivers coming from a population with a standard deviation of 5, we would expect our estimate of the population mean of speeding tickets based on the sample to be off by an average. On average, we would expect it to be off by plus or minus 1.581 speeding tickets. So doing what we did before, we would expect it to be between, 10 plus 1 standard error and 10 minus 1 standard error. So between 11.581 speeding tickets and 8.419. So the low end of the expected means from a sample size of 10 would be 8.419 up to the high end that we would expect 11.581. So you can see that when you have a situation where you have a smaller standard deviation, you also have a smaller standard error. And when you have a smaller standard error, you're expecting that your sample means will be closer to the population mean. Then when you have a situation with a larger standard error, and you have a larger standard deviation, which results in a larger standard error, and you're going to expect a bigger spread of your sample means from the population mean. Or in other words, you're expecting more sampling error when the scores in your population are spread out to begin with. Okay. Now this first one up here is the one we did before, so I already have the work done for you. But remember, before the only thing that changed between the two examples was the standard deviation. Well, now we're going to adjust the sample size to see what happens to the standard error. So this will demonstrate the relationship between the sample size and the standard error. So if we randomly select a sample of 400 drivers from this population with a mean of 10 and a standard deviation of 5 speeding tickets, how far away would we expect that sample mean to be from the population mean, just due to chance? So here's our standard error. We've got our standard deviation divided by the square root of n. Our standard deviation is 5, just like the example above. But now instead of having a sample size of 10, we have a huge sample size of 400. It's pretty big relative to a sample size of 10. So this becomes 5 divided by 20, and you end up with a standard error of 0.25. So in this example, with a sample of 400 drivers, our estimate of the population mean of speeding tickets based on the sample would be off, on average, by plus or minus 0.25 speeding tickets. So we would expect it to be anywhere between, so 10 minus 0.25, so 9.75, and 10.25 speeding tickets. So minimal error there, right? Really small margin of error that we would expect to see between any given sample mean from 400 drivers and the population mean of 10. Because we had a really large sample size. So our error is smaller because you expect that a larger sample is going to be more representative of the population. So this one's kind of tricky because you really have to think about how to manipulate the standard error formula to get what you want. So sometimes, prior to conducting a study, you should estimate the sample size needed to have a certain degree of error that you're willing to accept or to have minimal error. Now, this type of calculation can be innocent, where you're just trying to see, okay, I'm only willing to accept this amount of error between my sample mean and my population mean because I want my sample to represent my population. Okay, how large does my sample need to be? But sometimes researchers can have a really large sample size, have a really small standard error, and then end up with a really large test statistic and then get significant results, even if there's a really, really, really small effect of their independent variable and their dependent variable. Because think about the standard error. The standard error is in the denominator of the z formula. So if you have a really small standard error, then your overall value for your z-scores are going to typically be larger and more extreme. So then you would be able to say, oh, I did something to the sample. Now my sample means extreme. It doesn't represent the population. But it could just be because you had a really, really large sample. So any difference is going to be considered pretty extreme. So that'll be more relevant when we get to hypothesis testing, but I just wanted to mention it here as well. Okay, so if you want to have a situation where you want to have a standard error that's less than 15, and you want to know what sample size would I need to have to make that happen. All right, so here's one way that you could think about writing this out. So you could say, I want my standard error to be less than 15. So what that means, if you think about the standard error formula, you want your standard error to be less than 15. So you want 15 to be greater than your standard error. Well, another way that you could write this would be with the formula. So you could say, I want 15 to be larger than my standard deviation divided by the square root of my sample size. Well, we know the standard deviation, so let's go ahead and rewrite this, replacing standard deviation with 100. So we want 15 to be larger than 100 divided by the square root of this mysterious sample size that we are trying to figure out. So now you can algebraically manipulate this equation to get what you want. So we can multiply both sides by the square root of n to get rid of the denominator on the right side of this inequality. So we'll end up with 15 times the square root of n is greater than 100. Well, now we can divide both sides by 15 to get rid of the 15 times the square root of n, because we're trying to isolate n on one side of the inequality here. So we end up with the square root of n is greater than, and 10 divided by 15 gives you, 100 divided by 15 gives you 6.667. Now, we want to have something that says n is greater than something, right? But we got to get rid of this square root. So we can square both sides, right? We're doing the inverse operation. The inverse operation of squaring is the inverse operation of square root is squaring. And we end up with n needs to be greater than 44.445. Or, n needs to be greater than 45, because you can't have a fraction of a participant. So, with this population with a mean of 500 and a standard deviation of 100, you would need to have at least 45 people in your sample to have a standard error that's less than 15. Now, for those of you who aren't super comfortable with algebra and manipulating equations, I'm going to give you a beautiful little shortcut that you can use to figure this out. So instead of doing all this up here, you can simply use this. N needs to be greater than the standard deviation for the population divided by the desired standard deviation, standard error. So I'll call it the standard error that we want it to be less than. That whole thing squared. So let's try it with this less than 15 example. So n needs to be greater than, so the standard deviation for the population is 100. The standard error that we want the standard error to be less than is 15. Then we're going to square that. So this becomes n is greater than, remember 100 divided by 15 gives you 6.667. We're going to square that, and we still end up with n needs to be greater than 44.455, or 45. So if you're in a situation where you need to determine the minimum sample size to have a standard error less than some particular value, I would recommend using this formula right here. All right, now let's do for less than 10, and let's jump straight to the easier formula. So n needs to be greater than the standard deviation divided by the desired minimum value for the standard error, and then squared. All right, so this becomes n needs to be greater than, my standard deviation for my population is still 100. But now we want our standard error to be less than 10. So this becomes n is greater than, so 100 divided by 10 is 10. 10 squared, n needs to be greater than 100 to have a standard error less than 10. So, based on what I mentioned before, whenever you have a larger sample size, you're going to have a smaller standard error. So, if you start off with, oh, I want to have this standard error, or nothing more than this standard error, when you shrink that value down, when you're starting to be willing to accept less error, you're going to need a bigger sample size to achieve less standard error. So again, that's just an example of how you can use the standard error formula to figure out the sample size that you should shoot for to have a minimal amount of error. Okay, now let's move on to an example where we're going to calculate a z-score to figure out if Kaplan improves scores on the SAT. So in a previous lecture, you saw that with the scientific process, usually we try to take a random sample in hopes that those people represent the population. And then in an experiment, we do something to that sample. So we manipulate the independent variable, and we hope that after we manipulate the independent variable, that sample no longer represents the population because we did something to the sample that changed their scores on the dependent variable. And then if that's the case, we can be somewhat confident that whatever we manipulated actually had an effect. So in this example, we took a random sample of 25 students, gave them the Kaplan SAT test prep course. And now we want to see, all right, we assumed that the sample represented the population on the SAT scores before they took Kaplan. Now we give them Kaplan, and we're going to compare their mean on the SAT scores after Kaplan to the population mean. And if we find that the mean for the Kaplan students would be highly unlikely to have come from the population, then we can say, oh, well, these Kaplan students represent this new population of everybody who takes Kaplan, and that they don't represent the regular population who didn't take Kaplan. So in other words, if these Kaplan students have an extremely high z-score, then I would be inclined to recommend that students use Kaplan test prep to do better on the SAT because it puts them into this new category where they are far above and beyond what the US population is getting on the SAT. Okay, so I'm going to go ahead and draw a picture of this distribution first. Now I'm going to draw two distributions here just to show you the difference. So the first one that I'm going to draw will be the population distribution. And you should be familiar with this. So we would have the number of students along the y-axis, or the frequencies. Again, we're going to assume normal curves. And we know that the mean for the population of SAT test takers is 500. And with a standard deviation of 100, that means that most scores are between 400 and 600. But when we are talking about samples, we need to draw the sampling distribution. So the sampling distribution, the distribution of sample means. All right. So we have a sample of 25 Kaplan students, but we're going to assume that our sampling distribution is normal even though we don't have a sample size of 30 or greater because our population distribution is normal. So we still have number of students for our frequency or y-axis. Now our midpoint is still going to be the population mean because remember the mean for the sampling distribution is equal to the population mean. But now the spread or the variability of this distribution is no longer dictated by the population standard deviation. It's determined by the standard error. So we need to figure out the standard error. So how far of a spread do we expect to see in our means of sample size 25? All right, standard deviation divided by the square root of the sample size. Population standard deviation is 100, and our sample size is 25. So this becomes 100 divided by 5, and you end up with 20 as your standard error. So now, when we're talking about the sampling distribution, we would expect our sample means to be anywhere between, so one standard error below, so 480, one above, 520. And we're going to have a skinnier distribution than we did for the population. Because once you start looking at sample means, you're going to expect less differences from the population mean. Because if you're just looking at one person at a time, one score at a time, you're going to expect a wide range of differences. But when you have multiple scores coming from the population, you have more information about the population, you expect there to be less error, so you're going to have a skinnier distribution, less variability in your distribution. So this is the distribution that we're looking at right now. To figure out is this sample of 25 Kaplan students, is their mean on the SAT extreme? And in this case, the independent variable is the Kaplan test prep. The dependent variable, the thing that we're measuring, are SAT scores. So let's go ahead and calculate the z-score for this sample mean. So z equals the sample mean minus the population mean divided by the standard error. So the sample mean is 550. Population mean is 500. And then the standard error is 20. So 550 minus 500 is 50. Then we're going to divide that by 20. Now I'm going to pause for a second and explain this right here. The numerator that you see here, this 50, that's the actual difference between the sample mean and the population mean. Then the denominator, the standard error, is the difference that you would expect to see just due to chance, even if Kaplan had no effect whatsoever. Because it's not enough to say, oh, well, my sample mean is larger than my population mean, so Kaplan worked. Because you always expect some sort of difference between your sample mean and your population mean. How much difference do we expect? A 20-point difference. So the real question is, if you're going to decide to, take a Kaplan test prep based on this data, it's really expensive. You want to make sure it's actually working. You need to compare the observed difference between the sample mean and the population mean to that expected difference. And then if the observed difference far exceeds the expected difference, then we can be confident that it's not just some random chance difference that resulted in our means being a different value, but that it is some systematic difference, that whatever we did actually did have an effect, and that's why our mean is so much different. So 50 divided by 20 gives you 2.5. That's our z-score. So if we were drawing our values here, so the z-score for 500 would be 0 because that's our population mean. 480 would be -1 because that's one standard error below. 520, one standard error above. So our Kaplan students who got a 550, they're like out here, right? With a z-score of 2.5. They're really extreme. They're in a really low frequency part of the distribution, and we know that they're extreme because they have a z-score with an absolute value of 2 or greater. So we would say yes, the sample of students is extreme and does not represent the population of SAT test takers because now they're better than the population because they took Kaplan test prep. So this is a very close example to what you're going to be doing when we do hypothesis testing. The only difference is we're going to have a specific value that z has to meet to be called significant. And if it's significant, then we would be confident that it's not just some random difference that resulted in the difference between the sample mean and the population mean, but that the independent variable actually had an effect. All right, so now let's take a look at an example where we are trying to figure out the probabilities associated with specific sample means. So we are starting with a sample mean. We're going to calculate the z-score. Then we're going to go to the unit normal table and find the probability associated with that sample mean or range of sample means. All right, so we're still using the SAT distribution with a mean of 500 and a standard deviation of 100. And we're looking at the probability of randomly selecting one of these three options, A, B, or C, when we have 25 SAT test takers. So for part A, we want to know how likely would it be if we took a sample of 25 SAT test takers, how likely would it be for us to get a mean on the SAT of more than 550? All right, so we need to first find our z-score. But before we can find our z-score, we need to know what the standard error is. Because if you look at the z formula, z equals the sample mean minus the population mean divided by the standard error. Now, a common mistake that students make, they're fine with putting, the sample mean minus the population mean in the numerator, but then they just jump and put the standard deviation in the denominator. Don't do that, because we aren't looking at scores anymore. We're looking at means, and the measure of expected differences is going to be the standard error, not the standard deviation. Okay, so I'm going to go ahead and find my standard error over to the side here because I'm going to use that standard error for all three of these examples because I'm going to be working with the same population standard deviation and the same sample size of 25. So the difference that I would expect to see between any given sample mean from 25 SAT test takers and the population mean of 500 would be equal to the standard deviation divided by the square root of n, which is 100 divided by the square root of 25. So 100 divided by the square root of 25 becomes 100 divided by 5, which is 20. So on average, we would expect that any sample mean of 25 SAT test takers would have a sample mean that's about 20 points away from the population mean of 500. So, we would expect, if we draw our sampling distribution, like you saw before, anywhere between 480 and 520 would be our sample mean. All right. Let's put my z-scores in there. So for a mean of 550, what would be our z-score? So we've got 550 minus the population mean of 500 divided by the standard error that we just found, 20. You end up with 50 divided by 20, which is 2.5. So that is the z-score for part A. Now, I'm going to go ahead and find all my z-scores and then find all my probabilities. So for part B, my z-score would be, well, for 550 is still our mean of interest, my z-score is still going to be 2.5. I just found that, right? These have the same values. Only one we're going to look in the body and one we're going to look in the tail. All right, now part C. So now we want to see how likely it would be with a sample of 25 to get a mean between 450 and 525. So we need to find two z-scores. So we need to find the z for x equals 450. I'm sorry. See, there I go with my x values again. We're looking at means now. Mean of 450. And the z-score for a mean of 525. So for the first one, 450 minus the population mean of 500 divided by the standard error of 20, you get negative 50 over 20, which is negative 2.5. And then for a mean of 525, so 525 minus 500 divided by 20, you have 25 divided by 20, and you end up with a z-score of 1.25. Alrighty. So now let's go ahead and figure out our proportions, our probabilities that we're looking at. So for part A and B, we've got the same picture, right? So we've got our mean in the middle, which is 500. And in both cases, our score of interest is 550, which is right here-ish. And remember, the z-score for our population mean is always 0. And we found our z-score for a sample mean of 550 to be 2.5. So for part A, we're looking at greater than 550. So we're looking at a tail. But for part B, we're looking for less than or equal to 550. So we're looking for all the scores here. What's the proportion or the probability of randomly selecting a score in this end of the distribution? That is a body. So we're going to locate 2.5 z-score in the unit normal table and then find the proportion in the tail for part A and the proportion, tail for part A and the proportion in the body for part B. All right. Let's find 2.5 in our table. Okay, getting warmer. Aha! Z-score of 2.5. The proportion in the body is 0.9938 and the proportion in the tail is 0.0062. So let me put that in here. So for part A, 0.0062, that's equal to P of a mean greater than 550. Let's go ahead and circle that. And then for this one, we're looking at 0.9938 is the probability of randomly selecting a mean less than or equal to 550. All right. Now, one thing that you can notice, if you already found the probability of randomly selecting a mean greater than 550, and you know that this is the probability, well, then to find the probability of selecting anything else, right? Because if it's not greater than 550, it's less than or equal to 550, you could have literally taken 1 minus 0.0062, and you would have gotten this. Think about that. This represents 100% of all the means, or a proportion of 1. So if this represents 1, this whole thing, and you want to figure out everything other than what's greater than 550, or in other words, less than or equal to 550, you could take 1, all of this, and then subtract this proportion here and end up with that. Just a quick little conceptual note there. All right, so now we want to find what is between 450 and 525. So let me go ahead and mark this on the distribution down at the bottom right. So 450 is like here-ish, 450. And we know that that z-score is negative 2.5. And then 525 is about here-ish, 525, with the z-score of 1.25. So we're looking for everything between these two scores. Now, in the lecture where you were looking at finding probabilities associated with x values based on z, I showed you every which way to figure this out. This time, I'm just going to show you the easy way, which in my opinion is to take the mean to z for a z-score of 1.25 and the mean to z for a z-score of negative 2.5 and add those puppies together to get the entire thing. All right, so the proportion between the mean and z for each of these z-scores. So let's go ahead and go to our unit normal table. 2.5. Proportion between mean and z is 0.4938. So 0.4938. And that gives you all of this between the mean and a z of 2.5. Remember, no negatives in the table, but it's a mirror image, so it doesn't matter. Now let's figure out proportion between mean and z for a z-score of 1.25. All right. Keep going. All right. 1.25, mean to z, 0.3944. So 0.3944. And that gives you this. So you add those two together to get the total proportion between 450 and 520, or between a z-score of negative 2.5 and 1.25, and you end up with 0.8882. And that would be your final answer for part C. So you can look at this and you can turn these into percentages. I like to explain things in terms of percentages. It makes it a little easier. So you have a, this times 100, 0.62% chance of randomly getting a mean that's greater than 550 in this sample of SAT test takers. You have a 99.38% chance of randomly selecting a sample of 25 SAT takers with SAT test takers with a mean less than or equal to 550. So if you go back and you think about that example that we did earlier, where we saw that our sample was extreme, well, how extreme are they? Well, there is only a 0.62% chance of getting this score or higher in this population. So pretty darn extreme. The more extreme a z-score, the more unlikely a score of that or greater than, or in this end, that or less than is going to be. Okay, this one, you could turn this into percent and say there's an 88.82% chance of randomly getting a sample of 25 SAT test takers who had a mean on the SAT of 80 or of between 450 and 520. So pretty darn likely to get a sample mean that looks like that. Okay. So now let's move on to a situation where you start with a specific proportion. You go to the table to find the z-score. Then you use that z-score to calculate your sample mean. So we're still using the SAT score distribution, but now we're giving you specific proportions or percentages. All right, so for part A, I'm going to go ahead and draw this first. So we're looking for the middle 50% of the sampling distribution. So here's our sampling distribution. Here's our mean of the sampling distribution, which is equal to the mean of the population. And let's see, the middle 50%. So that would kind of be like here and here. Because you can think about this as 100%. So you've got 25%, 25%, 25%, and 25%, right? 4 times 25% gives you 100%. You can kind of think of it like a pie chart, right? You're just kind of segmenting it. So roughly the middle 50% is right here. So let's go ahead and shade that in. And we want to know what score is located at the high end of that middle 50% and what score is located at the low end of that middle 50%. There's a ton of ways that you could use the table to figure this out. I'm going to show you the easiest way to do it, which would be you to use the mean to z column. So if this represents the middle 50%, this is equal to p equals 0.50, right? Well, if I'm going to use the mean to z column, I need to split this up so that I have what's here and then what's here. So on each side of the mean, because we're splitting this in half, 0.50 divided by 2, you have p equals 0.25 from the mean to this z and from the mean to this z on the left side. So let's go ahead and find p equals 0.25 between the mean and z to then figure out what our z-score actually is for that location. All right. So we're looking in the mean to z column, and we're looking for 0.25. Dun, dun, dun. Looking for the one just below and the one just above, and trying to determine which one's closer to 0.25. Well, this one is 0.0014 away from 0.25. This one's 0.0017 away from 0.25. So this one's closer. So that gives us a z-score of 0.67. But not only 0.67, right? Because it's on both sides of the mean. So 0.67 and negative 0.67. Those are our z-scores here. Let's fill those puppies in. But what we want to know, what is the x value that corresponds to a z-score of negative 0.67? And what is the x value that corresponds to a z-score of positive 0.67? So we need to use our mean formula, which is equal to z times the standard error plus the population mean. This is really similar to the formula that we used to find x based on z. Remember, we had x equals z times the standard deviation plus the population mean. Only now we've replaced x with m because we're finding a mean, and we've replaced standard deviation with the standard error. Okay. So first we need to figure out the standard error. I've already figured it out in the previous problem, but let's do it again for kicks. So the standard error is equal to standard deviation divided by the square root of n, which is equal to 100 divided by the square root of 600 and, oh, this is a new one because we have a new sample size. So 625. So this becomes 100 divided by 25, which gives you a standard error of 4. Notice how this standard error of 4 is really small compared to the standard error that we had when we had a sample size of 25, right? The standard error was 20 in this example because we had a smaller sample size. Now we have quite a large sample size, and we're expecting a lot less error between our sample mean and our population mean. So now let's plug in our values. So we've got for this first, let's go with the low end first. Negative 0.67 is z times our standard error of 4 plus our population mean of 500. Negative 0.67 times 4 gives you negative 2.68. And negative 2.68 plus 500 gives you a mean of 497.32. So that's the mean on the low end of the middle 50%. So 497.32 right there. Now let's find the mean that's on the high end. So we have, let me go ahead, I'll put a little box around this one. Now we're going to do another one. So this is going to be the low end. Now let's do the high end. So now we're going to have positive 0.67 times 4 plus 500, which gives us 2.68 plus 500, 502.68 is the mean for the high end. So squeeze it in there, 502.68. So that would be your answer. The middle 50% of the distribution falls between an SAT score, a mean for the SATs, if you have a sample size of 625, of between 497.32 and 502.68. So you would have a 50% chance of randomly getting a sample mean, if your sample size was 625, between 502.68 and 497.32. All right, now let's do part B. Still using our standard error of 4 because we still have our standard deviation of 100 and our sample size of 625. So now we're looking for the top 10% of the sampling distribution. This would be like, the score at the 90th percentile, in other words, if we were looking at scores. So I've got my distribution. I know that my mean is my population mean in the middle, 500, and I'm looking for the top 10%. So that's roughly here-ish. So I need to find the z-score that corresponds to p equals 0.10 in the tail. I could also look for p equals so what's left, 0.90 in the body. Either way you go, you're going to get the same exact z-score. So let's go ahead and look at our table and see what we find. So I'm going to go ahead and look at the tail. So I'm going to keep going. It's getting smaller. Oh, getting closer. So this one's just above 0.10. This one's just below 0.10. This one is closer to 0.10 than this one. This one's 0.0003 away. This one's 0.0015 away. So I'm going to go with this z-score, which is 1.28. So for this one, z equals 1.28. So if I fill in my values in my table, remember, the mean's always got a z-score of 0, 1.2, oh, we don't want to put it there, we want to put it where z goes. 1.28 is right here. Now we just plug in that z-score and our mean and standard deviation from the population into the mean formula. So z times standard error plus the population mean. So 1.28 times the population standard deviation, whoops, the standard error of 4 plus sample mean of 5, or the population mean of 500. So 1.28 times 4 gives you 5.12. Add that to the population mean of 500, and you get 505.12. That is the sample mean that starts the top 10% of all sample means. So 505.12 would be the mean right here. So any mean above 505.12 is in the top 10% of the sampling distribution. Another way that you could think about this for part B is that you have a 10% chance of randomly selecting a sample of 625 SAT test takers who have a mean on the SAT greater than 505.12. All right, let's go ahead and do part C. So I'm going to erase some of this. Time for part C. Okay, so for part C, we want to look at kind of the sadder end of the distribution, right? For part B, we were looking at the really high scores. Now we want to look at the bottom 30% of the distribution. So this would be akin to the 30th percentile, if you remember doing percentiles before. All right. So now we have a distribution where we still have our population mean right in the middle, that 500. But the bottom 30% would be a score right around here-ish. So we could either look for p equals 0.30 in the tail, or we could look for p equals 0.70, right? 1 minus 0.30 is 0.70 in the body. Either way you go about doing it, you're going to land on the same z-score. So let's go ahead and find 0.30 in the tail. All right, keep on going. Oh, this one's just above, this one's just below 0.30 in the tail. This one is closer to 0.30. This is 0.0015 points away from what we're looking for from 0.30. This one's 0.0019 points away from 0.30. Same thing would happen if you were looking for 0.70 in the body, right? This one's closer to 0.70 than this one. Either way you go about doing it, you land on a z-score of 0.52. So I'm going to write down z equals 0.5. Whoop, that's a 4. 0.52. Now, because I'm a good student and I drew my pretty picture, I would be able to stop myself right here and go, wait a second. The score we're looking for is to the left of the mean. So I'm going to have a negative z-score. And that's really important when you go to plug this into the formula for the mean, because you know that the mean you're looking for is going to be less than the population mean. I think I said score before. I'm still stuck on scores. All right. So with our formula, the mean is equal to z times standard error plus the population mean. So we've got negative 0.52 times the standard error that we found before, which is 4, plus the population mean of 500. Negative 0.52 times 4 gives you negative 2.08. Add that to 500, and we know that we have a mean of 497.92. So if we filled in this distribution, these are our mean values, these are our z values. The z-score of negative 0.52 corresponds to a sample mean of 497.92 if we have a sample size of 625. So any mean below 497.92 is in the bottom 30% of the sampling distribution. Or we could say there's a 30% chance of randomly selecting a mean of 625 SAT test takers whose sample mean was less than or equal to 497.92. All right, let's do another example. I'm just giving you tons of examples today because I think it's really important for you to understand how to do this. And it can be kind of tricky. Even though it's kind of review of what we've done in the past, it's important to remember it's the standard error that's the foundation for this, not the standard deviation. Okay, so now I'm going to give you an example where we have the same mean and standard deviation from the population, and we're also interested in the same mean as the starting point, 75. But now we're going to look at situations with different sample sizes. All right, so on average, it takes people 70 seconds to brush their teeth with a standard deviation of 20 seconds. What is the probability of randomly obtaining samples of individuals where the mean brushing time is greater than 75 seconds when you have a sample size of 4, 16, or 100? So for part A, And I'm going to do each step for each one of these separately. All right, so for part A, we need to first figure out what is the standard error. Because first thing, the standard error is going to be the denominator of our z-score, and the standard error allows us to draw our distribution appropriately. So our standard error is going to be equal to, so our standard deviation divided by the square root of our sample size. Whoop, I stuck 4 in there. Let's go ahead and start with symbols and then start putting numbers into it. All right, standard deviation is 20. 4 is our sample size in part A. This becomes 20 divided by 2. We have a standard error of 10. So for any given sample size of 4 people, we would expect that their sample mean would be within 10 seconds of our population mean of 70. So if I drew this distribution out, it would look like this. Assuming a normal curve, our population mean in the middle of 70, and then we would expect our sample means to fall between 60 and 80, right? One standard error away from the mean. All right, now let's look at the distribution in part B. So the standard error in part B is equal to, standard deviation is still 20. We're still working with the same population. But now our sample size is 16. This becomes 20 divided by 4. And 20 divided by 4 gives you 5 for the standard error. So, as you can expect, the sample size is increasing, our standard error is decreasing, and the variability in our sampling distribution is decreasing. So 70 is still our mean, but now we're expecting scores to be between 65 and 75. So we have a skinnier distribution than before. Part C. Standard error when we have a sample size of 100. So 20 is our standard deviation, sample size of 100. This becomes 20 divided by 10, and 2 is our standard error. Even smaller than the standard error for part B because now we have an even larger sample. So in this one, our mean is still 70, right? Population mean is equal to the mean of the sampling distribution. But now we're expecting people to have between, or our sample mean to be between 68 and 72. So we have an even skinnier distribution than for part B because our standard error is smaller due to the fact that we have a larger sample size in this example. So we've got our standard errors, we've got our distributions drawn out. Now we need to figure out our z-scores so that we can then go to the table and figure out our probabilities. Now before we get to that, let's go ahead and sketch where our probability would be in this example. So I'm looking at this and we're looking at greater than 75. So 75 would be about here in this distribution. Greater than 75 is a tail. 75 is here in this distribution. This is also going to be a tail. And 75 is like way out here in this distribution. So we're also looking for a tail here. Now just visualizing this before we find our z-scores and before we go and find our probabilities, you can probably guess that we're going to have a smaller probability here, followed by this probability, and then the most likely probability here. Just looking at the pictures. So now let's go ahead and calculate our z-scores based on what we found before. And I'm just going to quickly jot down some information just to remind me of what we were doing. So we had a population mean of 70, we had a standard deviation of 20, which part A we had a sample size of 4, which resulted in a standard error of 10. In part B, we had a sample size of 16, which gave us a standard error of 5. And in part C, we had a sample size of 100, which gave us a standard error of 2. All right, ready to roll. Let's find our z-scores. Oh, and we're looking for mean greater than 75. Now, I know I'm not very good at drawing mu's, and my mean and my mu looks pretty darn similar. Let me try a little harder. Just as a rule, when I draw my m for my sample mean, I try to make sure that the middle and the sides kind of touch in the same place, like they land on the same line. For my mu's, it's just kind of curly. But I'm sorry if that confuses you. I'm not very good at drawing mu's. Okay, finding z's. So for part A, remember our z is equal to the sample mean minus the population mean divided by the standard error. And in all of these cases, 75 is the sample mean of interest, 70 is the population mean, and the standard error changes based on the different sample sizes. So in this one, we have 10, whereas in part B, z is equal to 75 minus 70 divided by the standard error for part B was 5. And for C, remember, still have the same sample mean and population mean in the numerator. It's just the standard error that's changing. All right, so 75 minus 70 is 5 divided by 10 is 0.5. That's our z-score when we have a sample size of 4. Now let's find our sample size, or our z-score when we have a sample size of 16. So 75 minus 70 is still 5, but now we're dividing it by the standard error of 5. We get a z-score of 1. Then part C, when we have a sample size of 100, 75 minus 70 is still 5, but now we're dividing it by 2, and we end up with a z-score of 2.5. I'm going to color code A as red, B as green, and C as blue. And let's go back and look at our distributions real quick. So you can pretty much see that, yeah, for part A, the z-score was smaller because relative to the standard spread of means from sample means from the population mean, 75 is relatively closer than 75 is for these other distributions. So for this one, for part B, 75 is one standard error away from the mean, right? It's 1/5 away. So when you look at the picture, it's right at, where you would expect, at the high end of where you would expect means to fall. Then a 75 in this distribution has a really large z-score because it's rather extreme, right? It goes way out past the range of sample means you would expect to see just due to chance. Now let's find our probabilities. So in all of these cases, we're looking in the tail. So we're going to find our probabilities here. All right. So if we look for z of 0.5 and the proportion in the tail. So 0.5, 0.3085 is what we end up with. So 0.3085. When we have a z-score of 1, the probability of getting greater than 75 seconds, tail 0.1587. 0.1587. And then for part C, when you have a sample size of 100 and a z-score of 2.5, then you know the probability of getting a sample mean that's greater than 75 is, oh, the suspense is killing me. Okay, 0.0062. 0.0062. So when you look at this example, you can see that it's much less likely to sample 100 people whose toothbrushing time exceeds 75 than it is to sample 16 or 4 individuals with a mean greater than 75. Now this is because the large sample results in a low standard error, which results in a low chance of obtaining a sample that doesn't represent the population. So as your sample size increases it becomes less and less likely to get those extreme scores because you think, oh, you have a big sample size, you should be representing the sample mean with that sample. Or, sorry, representing the population mean with that sample mean. So this kind of shows you, as the z-score increases, the probabilities in the tail decrease, and that also mimics the pictures that you see here, right? It's getting less and less likely to get that sample mean. So I know I threw a ton of examples at you, but I want to make sure you really understand how to use these tables, make sure you understand the standard error, and that you feel really comfortable with all the formulas that you're going to be using in this chapter.